Welcome to another episode of Code for Thought. In this episode, we'll talk about graphs. The concept of graphs has been around for quite some time. For instance, the Handbook of Graph Theory traces the origins back to Leonhard Euler in the 18th century. In computing, graphs are usually associated with their use in social networks, but that's only the tip of the iceberg. Graphs can be used and are used in a variety of applications in commerce as well as science. And in recent years, we've seen a proliferation of tools like graph query languages and graph databases. Which brings me to Ben Steer and Gabor Szarnyas, who've both been working in this exciting area for some time. In the following interview, we touch on some of the projects they're involved with. And since there's a lot to talk about when it comes to graphs, it will be a little bit longer than usual. Let's start with the introductions.
I'm Ben Steer. I've a recent PhD graduate from Queen Mary University in London, and I'm working on a project for the Alan Turing Institute called Raftery, which is for distributed graph analytics with a temporal component, so looking at graphs through time. I'm a co-founder at Choreograph, where we're attempting to productize Raftery and turn it into a tool that lots of people can use. And I work with Gabor at the Linked Data Benchmark Council, looking at standardizing benchmarks for graph systems, standardizing graph models and query languages and all that fun stuff.
Gabor.
Hi, I'm Gabor Szarnyas. I am a postdoctoral researcher at CWI Amsterdam in the Database Architectures group. I did my PhD at the Technical University of Budapest, focusing on graph models, and this led me to the work of graph analytics and graph databases. So these days I spend my time on working on more efficient graph analytical techniques in the part of the GraphBlast collaboration, and I work in the Linked Data Benchmark Council as the task force lead of the benchmark task force, where I work with Ben.
Thanks very much. So let's start very much from the basic level. Could you start by giving us a high-level overview what graphs actually are?
Graphs are these well-known mathematical constructs which consist of a bunch of nodes and connections between these nodes known as edges. And this data structure has been around for more than 300 years, so it's very common and it's very powerful already. You can model things like a logistical network, a social network, and many similar network of nodes. But it has been observed that this is not really expressive enough. For example, if you think about a social network, it's not just people who are acquaintances. There are more subtleties. Some people are colleagues, some people are family members, others can be friends. It might be worth introducing additional data on the edges. This is often in the form of labels by describing what the connection actually is. And these labels can be applied to nodes, which is already a lot more expressive. What really kickstarted the movement of graph databases is realizing that both the nodes and the edges can also be annotated with the so-called properties, which are basically attribute informations. In a social network, a person has a name, a person has a birth date, a connection between two people has a creation date, where that particular creation was instantiated in the social network. And this is a very expressive model to work with. And people have found this very intuitive to use for modeling their problem domains and reasoning about their problems.
The main thing to add on to the bottom of what Gabor was saying there with graphs is that they are sort of, once you sort of swap your brain into this way of thinking, they're a very intuitive way of sort of reasoning about your data. You know, most of the ways that people view data at the moment is, if you look at something like, well, let's go from the basics of CSVs or like Excel files, or if you're doing something, say, slightly more advanced, if you're looking at like a data frame or something in Spark, like an RDD, you're reasoning about individual lines of information. And intrinsically, what's going on under your data set is you have entities that exist in that data and you have relations between them. So in Gabor was saying about a social network, you have people interacting. But if you're looking at, say, transaction networks, you have wallets or businesses or people and them transacting with each other. That, you know, most data can inherently be modeled as a graph. When you start thinking about it in this way, you get out a lot of insights, or like the sort of questions that you're asking become a lot more apparent.
So what advantages do graphs actually have over relational databases?
I would take this one initially, but I think this is definitely Gabor's space to shine. I think my feeling here is that definitely the way, going back to the previous point, is the way that you can kind of model data and the way you can reason about it from a querying perspective. I think at the moment, I would say that the relational world, to be fair, has had a good amount of head start. People will say things like, "Oh, well, in a graph database or in graph systems, you don't need to do lots of joins. This is a big issue with relational databases and so on." A lot of these features, I think, you can still cover somewhat nicely in a relational database. The problem is that the sort of query languages that you're using and the way you're reasoning about the data is not really correct for the sort of queries that you'd be doing on graphs. So there's a lot of kind of interesting issues, things like recommendations and shortest paths and all this sort of stuff that are, I'd say, very, very unpleasant to do in relational databases. I think once the dust settles through things like the LDBC, where we can kind of sort of standardize some of these elements, that's when you'll see graph databases start to take off past the relational threshold that currently exists.
Gabor?
I would say I use 2 litmus tests to decide whether to use a graph database. The first one was mentioned by the CEO of the Neo4j company, and this is that you should think about how you explain your model. If you would explain your model to someone else in front of a whiteboard by drawing a table with tabular data, for example, you have weather data and you report on a particular amount of precipitation on a given day, then this is clearly a tabular data and the relational database is perfect for the job. But if you draw some sort of nodes and edges on the whiteboard and explain your model in terms of the connection between your entities, then it might be worth using a graph database. On the programming side, it's often found that people already store their data in a relational database, but it actually represents a graph. And this can work for quite a while, but you often start doing graph operations outside of your database. For example, if your data represents some sort of a network of nodes, you might want to run a centrality algorithm like PageRank or betweenness centrality. And in this case, the way to do this in a relational database is to extract the data and do this analytical computation elsewhere and find the important nodes and then continue the querying of those important nodes in the database. Or you can do some sort of a shortest path algorithm between 2 nodes. Some of this you might be able to push into a SQL database, but the syntax is a bit noisy, a bit cumbersome, and difficult to read. After a while, your code gets unmaintainable, so the SQL code can get noisy and the application code can be detached from the database. And in these cases, it's well worth considering changing to a graph database that could do these operations within the data processing engine.
So in short summary, so when you find that you have to actually do something outside your database in order to do some analytics to then proceed to actually get the data you want, which is something that graph databases could give you for free, then that might be sort of the kind of threshold where you need to decide to switch over to a graph database. Would that be a fair summary?
Yes, exactly. If you find that you are round-tripping a lot between your client and the database and you're doing data processing in the client code, then it's definitely worth asking the question whether this should be more efficiently done by the database. And the answer is often that the graph database could help.
When we talk about graphs, they've taken off quite a bit. We mentioned social networks. Where do graph databases and graphs enter science? And what kind of projects and use cases might there be where graphs might be useful?
I think it's interesting, actually, because I think that's actually where they've been picked up the most. I don't know if Gabor has a different opinion on that side of things, but from the people that we've been speaking to, I think you find that there's a lot of academics that tend to have very interesting data, and they're not so worried about how it's stored and are interested in doing sort of novel things on it, both from a publication perspective but also to understand kind of what's going on under the hood. We've spoken to people that want to do things like urban analytics, so looking at like track and trace, using graphs for things like COVID, but also for understanding why certain streets are used by women and other streets are used by men. There's work in things like word semantics, so building large networks of how words interact, are used in co-occurrence and talking to each other. So quite arcane uses of graphs and sort of stretching what you would consider like an entity to the very sort of limits. And these people are very open to it. I think the issue that there is on that side for a lot of the industry side of folks is that they have like 20 petabytes of data stored somewhere in an old relational database, and you say, here's all these cool new graphy features, and they go, yeah, that's fine, but it's a real pain in the ass for us to swap over to your new tool. On Gabor was saying, I think a lot of them have gone into this point of they'll keep their old relational database, they'll then pull that out into something like Spark or a variety of other tools that are used for graph analytics as like a middleman, which is totally fine. I mean, if that's all you're initially doing, but it does cause you problems in the long run. And even some of these analytical tools that are in between, they're not fit for purpose. Like Spark GraphX, for example, is not ideal if you want to do this stuff. There's a lot of better platforms that'll be so much quicker, but that they have to make this swap over.
Gabor?
I think graphs have been almost omnipresent in science, in social sciences, biology, and also current event-related sciences like epidemiology or modeling power grids. In fact, we have this whole field called network science, which deals with how graphs should be analyzed and how you can understand the emergent properties of a network. And network science does a lot of foundational research, trying to come up with new ways to model these processes and understand how these networks can be tackled at a mathematical level. But they also do a lot of applied research. For example, urban mobility is a very interesting topic when they try to model how cities work and how people navigate the streets of their cities, as Ben mentioned. And also we have interesting use cases in the pharmaceutics industry. For example, we have drug repurposing, which looks into drugs that are known not to have dangerous side effects and tries to find other uses for those drugs. And I believe this has been actually used during COVID-19.
That's an interesting subject, but I would like to move on to the tooling aspect, and particularly graph query languages, because there the landscape can be quite a little bit confusing and it looks quite fragmented. What does the landscape of query languages look like to you at this moment?
I think the fragmentation is true, and it stems from the very strong expressive power of graphs. The spectrum of the operations that you can do on a graph data structure is very wide, but I would say there are two major categories. One is graph analytics, which is often found in textbooks. You do operations like a depth-first search or community detection or determining connected components in a graph. And in this bucket, you usually have a static graph and you would like to determine some sort of algorithmical result by dividing the graph into components or communities or detecting cycles in case of a depth-first search. And these are usually very computationally intensive operations. On the other end of the spectrum, we have the graph database world, where the data is continuously mutated and the operations are more localized. So you don't do a big sweep through the graph. You rather find a particular node and maybe look around in its immediate neighborhood or second-degree neighborhood. In these cases, the system is often running in a transactional setup, so you get new updates possibly every second, and you would like to consider those updates in the results of your queries. And the analytical computations are usually defined in some sort of an imperative language or in some sort of a software library that people can readily use. The graph database space, on the other hand, uses various query languages like Neo4j's Cypher language, the upcoming GQL language, and the extension to the SQL query language, which is called SQL/PGQ.
The main addition I'd say there is that I think the analytical landscape is a little bit more steady in that the sort of imperative models that exist, things like thinking like a vertex, or so a vertex-centric processing, have become they're sort of quite popular. Or you have models based on linear algebra that, like GraphBlast that Gabor works on. There's not a huge amount of shift there. I think the interesting area really is in the graph querying languages, because things like the SQL standards kind of grew over quite a long period of time, and that's kind of what we're seeing now. So Cypher is a juggernaut in this space, but then TigerGraph have their own language that's becoming quite popular. You then have Gremlin, which is very popular because of the Tinkerpop stack, and a lot of academics will use that. There's a strong push, again, through the ALDBC to bring these together, all of the major players that are creating their own languages, and try to find some sort of standard equivalent to the SQL standard in a way of kind of just sort of maturing the graph industry as a whole. I don't know if Gabor, do you want to speak quickly about the GQL standard?
GQL has grown out of the notion that Cypher, the language of Neo4j, became very popular. A lot of the popularity of Cypher is attributed to how intuitive it is. It uses this ASCII art syntax with parentheses for the nodes and square brackets for the edges. And people found that this actually resembles the whiteboard modeling of graphs quite closely. It was open sourced in late 2015 called OpenCypher. Vendors have started to pick this up and started implementing their Cypher compatible engines, but it was soon realized that this is something bigger than just an open source specification, and efforts to standardize it has been started since then, and the new standard is expected to come out during next year. So GQL is going to be the first new standardized query language since SQL. So this has been like a 40-year gap between these two languages. And the whole goal of GQL is to make graph queries intuitive to use and allow for composable graph queries, meaning that you can run a query on your graph database, return another graph, and then pipe this into another query and do complex analytical tool chains. And obviously, many people do similar tool chains these days, but they usually build on something like Spark or Airflow. And GQL will unlock this possibility for graph databases in a very nice declarative language.
When it comes to standardization, there is always apart from the commendable effort behind it, there's also the question about how do you get the players on board and how do you actually convince them to accept that standard. For the commercial aspect of it, people may think that, why should I do that? Why should I sign up to that standard? I lock people into my ecosystem and then be damned if they don't use it. So what would your answer to that be?
I think you have said the magic word, lock people in the ecosystem. I believe people are extremely cautious and make steps to avoid vendor lock-in. So if they can pick a database that has a standards compliant query language, then they will pick that. So it's in the vendors' best interest to pursue the GQL compatible query layer. And LDBC, the Linked Data Benchmark Council, where we work on the benchmarks of the graph space, plays a big role in this area as well. It helps vendors to access early drafts of the GQL standard. They can make their opinions and contributions known. So it helps them to prepare for the adoption of this eventual standard.
I was going to just say, I think that kind of the real thing or issue that a lot of the database vendors for graphs are having is that, it's making a big switch for people. So if we can kind of all push together as a unit, it's beneficial for everyone. The query language standard is one part of that, but I think in general, if there is a big push by the graphy community to convince people, relational isn't always the only way. I mean, yes, it covers a lot of use cases, but there's, a wide plethora of extra things that graph can do for you.
Where do you see that whole evolution going then in the end? You mentioned GQL, and that's hopefully going to be a standard next year, you mentioned?
Yes, it's expected to come out in late 2022 or maybe early 2023. This will be one of the focal points of convergence, I believe. The other large strain is the SQL PGQ extension. So obviously, a lot of people will still keep their data in a relational database, but they want to do just some graphy operations on top of it. SQL PGQ is perfect for this job because you can define your vertex and edge views on top of the graph. And you can do 80% of the things that you could do with GQL, meaning you can do shortest path, pattern matching, you can do graph path queries in the form of regular expressions. And the syntax is already a lot more readable than in SQL, plain SQL and recursive SQL queries. So this will be one of the points of convergence for graph query languages. In the analytical space, I don't yet see such a language. There have been attempts to create nicer APIs, but this is such a general problem that it's very difficult to capture it in the form of a language. What I do expect is better graph analytical libraries. So it's unavoidable that people will want to utilize not just the multi-core CPU that their machine have, but also GPUs and other coprocessors that are
Indeed.
coming along in the next decade. And graph analytics libraries would better make good use of those hardware.
I'd like to move on to the next subject, which is benchmarking and performance for graphs. And you already mentioned the Linked Data Benchmark Council that I believe you're both involved with. Let's step back a little bit and talk about what that council actually is and what you do there.
In terms of database benchmarking, this is a decades-old problem. It's very difficult to assess the performance of a system before one starts using it. And because the whole field of graph databases is so nascent, people would like to critically assess the performance of graph databases before they start investing in setting up their own infrastructure based on graph databases. And this has been a problem for relational databases 3-4 decades ago. And the answer to that was establishing a benchmark council, which defined standard-ish way to test the performance of systems and also provided auditing guidelines to check whether a system has been properly benchmarked. This was very successful. The TPC, the Transaction Processing Performance Council, has revolutionized the whole database benchmarking space. And in the last 3 decades, there have been hundreds of TPC benchmarks, and they are kind of the de facto standards for relational database performance. Researchers in the early 2010s have realized that this is missing for graph databases, so they started LDBC, the Linked Data Benchmark Council, which aims to fulfill a similar role in the graph processing space as TPC did in the relational space. The initial vision behind LDBC was that it should provide benchmarks and auditing guidelines to facilitate fair competition between various graph database vendors. And this is still on our agenda. But while designing the benchmarks, people have realized that it's also important to invest in the API front and in the query language front. And this is what partially led to GQL and the PGQ language.
From my perspective, when I first started getting into graph analytics and building tools, I went to a conference called DEBS and I met some very lovely guys called Benjamin and Dom, who had also been building similar platforms. And we found that basically, as Gabor said, when we were looking at all of these graphs or this graph tech, everything was total apples and oranges. So no one would use the same type of machines, the same type of queries, the same data. And we thought, this is insane. Why don't we try to standardize this in some way? So we wrote a workshop paper for grades, which is a graph workshop at Sigmod. And when I turned up to present it, I met Gabor, and he said, what you're working on is interesting. However, there's lots of other people that are doing stuff on it. Why don't you come and join in? So one of the aspects that we were interested in was taking stuff like the LDBC social network benchmark, and which is initially for the interactive workload had a reasonable idea of like there's a sort of bulk ingestion of data, some insertions on top, but for the most part, the database isn't changing a huge amount. When you start streaming in the real world, data is changing constantly. You also have things like deletions and lots of other stuff going on. Can you start having a look at databases that can handle this a lot better? Then I got kind of involved in the general benchmark as a whole. So now looking at the business intelligence version of the benchmark. So much more complex graphy queries that really kind of show off why graphs are cool. And then integrating this element of micro batching and streaming into the benchmark, which I think hopefully is our kind of next big push.
How do you approach that kind of benchmarking process to say, this is good for this and this is good for that? Do you have any categories that you say, okay, we have these kind of major use cases that we measure it against, or how does this work?
From my perspective, Gabor was going to hate me for this because I think he probably categorized them slightly differently. But I think from the LDBC perspective, there's kind of 3 major categorizations that we have. So we have graphalytics. The model is very simple, so you don't tend to have very many properties, or it tends to be just like weights and so on. So this is when you've got like a big network, and in our case is just people and friendships, and then you do things like PageRank. These big, very difficult to process algorithms which involve basically all of the nodes on the graph going through all of the different paths and so on. Going kind of like to the in-between position, you have then the business intelligence queries, which are a lot more sort of faster paced. You may have data, changing in the background, and you start to bring in back all of these different types and properties. This can be things like closing off triangles. In the social network instance, it's like two people share a friend, but that person isn't a friend with one of them. So you want to close that link. And a variety of other slightly more difficulty graph problems. And then right on the other side, you then have what we call interactive. So these are very sort of small, easier to run queries, which are just like, I want to find like a friend of a friend that made this post, and stuff that can be viewed as slightly more relational. It's something that you can imagine to exist in a relational database. So I think we kind of broadly categorize them, but systems tend to fit across that spectrum. So you get some, say for example, Tiger, who are attempting to do very much the business intelligence, but also will offer all the graphalytics stuff. Same with Neo. So they initially started out more in the interactive space, but are now offering this additional like graph analytics libraries on top, which you can mix in with your queries.
I think Ben did a good job in summarizing that. And I would add that LDBC has many of the graph database vendors on its board. So we frequently talk to these vendors and we try to figure out what the interesting use cases are. The current 3 benchmarks were designed because at the time of their design, they were deemed important enough and critical enough to be benchmarked. And what's really important regarding benchmarks is that the benchmark is always an approximation of what would happen in a real system. And in order for a benchmark to be usable, it needs to be representative of some people's actual workload. So even though our benchmarks are called a social network benchmark, it's not just representative of social network performance, but also for similar workloads, similar transactional and analytical workloads. And we are keeping our eyes open. So if new fields are popping up within the graph processing space, we will add new benchmarks. A prime candidate for this is the world of graph neural networks, streaming graphs, various other temporal graph processing problems. There is always a possibility of introducing new benchmarks. We are currently working on 2 new benchmarks, one coming from industry and one coming from academia.
Let's talk a little bit about the projects that you're actually currently involved with. Gabor, in previous discussions offline, you mentioned 2 projects, SQL PGQ, extension to Duck database, and LA Graph. Let's start with LA Graph. Could you tell us more about it?
This falls in the basket of graph analytics. There are numerous graph analytical systems that have been designed during the last 15 years. The most popular ones are iGraph, NetworkX, and Snap, the Stanford Network Analysis Platform. And these all tackle the problems of PageRank, other centrality algorithms, searches, shortest path, etc. But these libraries have been designed about 10 to 15 years ago, and they focus on single core processing. So there is no parallel processing support involved in these libraries. And it turns out that it's actually very difficult to make graph algorithms run in parallel. However, it is unavoidable because we have many core CPUs and the single core CPU performance has been stalled and is not going to take up in the near future. So we would better make sure that if you run a graph algorithm, it uses all the cores of a CPU. And there is a lot of exciting new hardware coming out, not just GPUs, but also other coprocessors, for example, Intel's Puma, which is a graph-dedicated ASIC. We have various other hardware for machine learning, for example, the Sambanova RDAs, the reconfigurable data flow arrays. And these are very much a good ground to build a graph processing application on top of. And what LA Graph tries to achieve is that it uses the GraphBLAS API. GraphBLAS defines standard building blocks in the language of sparse linear algebra. So if you work in sciences or data processing, you probably have heard of BLAS, the basic linear algebra subprograms. This was designed to standardize operations for dense linear algebra, and GraphBLAS does this for sparse linear algebra. But GraphBLAS is still kind of low level, so you need algorithm designer and programming experts to use it. And what LA Graphs will achieve is packing these GraphBLAS primitives into a more accessible library. So users without any deep understanding of linear algebra should be able to use this as another graph processing library and exploit all the performance that they can get from their machines.
Is that Project LA Graph? Is that something that people can look at? Is that open source?
Yes, so LA Graph is open source under the GraphBlast GitHub organization. And the work with respect to benchmarking is very interesting because I have basically implemented almost all of the LDBC benchmarks on top of GraphBlast. And this was very instructive because I could learn a lot about GraphBlast this way and find a lot of nuances and performance inefficiencies and challenges in using the API. What we are currently doing is adding more algorithms to this LA Graph library. So far, we have covered the LDBC Graphalytics benchmark, another benchmark from UC Berkeley called the GAP benchmark suite. And we are looking into introducing more and more algorithms in the near future.
Ben, we come to you now and Raftery, practical system for the analysis of temporal graphs. So let's just clarify what a temporal graph is and why do you want to analyze them?
It's everything that we've been talking about and added in an awful lot more complexity to make everything explode. The general idea of a temporal graph is that, so as we were saying, that when you have sort of real world data sets, new information is kind of streaming in a lot. So this will be updating properties, it will be adding new edges and nodes, and possibly even removing entities and their relations from the data. So what a temporal graph does is, instead of removing those or changing the properties over, it tracks all of the prior versions. For a given entity, you'll have a history of when it was created, when it was updated, and for their properties, you'll have previously my username was Bob, now it's Ben. And what we do in Raftery is allow you to then go back and explore that history. So that one aspect of that exploration is that you can say, okay, well, I want to know what the graph looks like now. I want to know what it looks like an hour ago, or some point, some exact point back in time. What prior systems tend to do with this is that they'll take snapshots, and they'll allow you to explore those, but this is kind of a much more fine, granular exploration of history. Another aspect of this that we're interested in is different temporal depths. So once you have this history, you can now start doing things like, okay, well, I'm looking at a set point of time. So let's say Tuesday at 3 a.m, but I only want to look back like an hour, a day, a week, a month, and a year. And I can run the same algorithm, so let's say PageRank, and see how my results vary. So now if you start doing that sort of stuff over time, you start seeing sort of long overarching stories of the data, which are kind of like the aggregate information. But in the short windows, so your days and your hours, you start to see like short-term trends and kind of what's actually happening. And that's been really interesting. We've looked at things like 400 years of legal citations and seen how papers become important initially, if they have some sort of lingering effect over time. You can actually start including this history in your queries. Going back to the financial example that Gabor was giving, you can have a look at things like temporal shortest path. But like if you're looking at money laundering or like cycles that happen in your network, you want these to happen in a time order. So if we have the three of us, if you say send me money, I send money to Gabor, and then Gabor sends money back to you, and this is all an hour apart, and this happens every Tuesday at the same time, then this is the sort of pattern that you're going to start to explore. The only problem with this, obviously, is that it's hard enough doing the graph pattern matching, motif extraction, and so on from a normal graph. When you start adding in, all the different possible time orders that this can happen, there's this huge explosion of possibilities. And why Raftery is still a work in progress, but soon this will be very available for everyone to have a crack at.
We're coming to the end of the podcast show now, but before we finish, if you're a novice in all of this, where would you start?
So there is an overview paper titled "The Future is Big Graphs, a community view on graph processing systems." And this paper was the outcome of a DAX2 seminar where I participated in late 2019. It talks about abstractions, query languages, performance issues, and many other topics that we have touched on today. So that's definitely a good starting point. If you are in the performance critical domain, I encourage you to check out LDBC's work. If you are in the sciences, you are probably already using some sort of a graph processing system. And if you're happy with that system, I encourage you to keep that system. If you find that you have performance problems, it's worth looking into alternatives because there has been a lot of developments in this space. So if you find that your Network X-based analytics takes hours, it might be worth to look for alternatives and try to find other libraries.
It's funny, actually. Gabor and I were talking about this yesterday. It's difficult to say because I think we kind of arrived at this point over 3 or 4 years of sort of organically having a read around and deciding what we found was interesting. I would double down on what Gabor was saying in that depending on what background you have, I think if you're interested from a maths perspective or from a science perspective, there's an awful lot of researchers out there for you to dive into network science. For people that perhaps a little bit more are tepid in that regard, I think my advice would be is that have a look at whatever it is that you're working on, so whatever data set you have, and start thinking about, is there a network that I can extract out? What are the entities that I'm interested in? At that point, can you then bring that into one of the tools that are available? And it doesn't have to be something fancy. I mean, well, Neo4j, takes 5 minutes to set up. Or alternatively, if you like Python, things like NetworkX and Gephi and these other really easy to use platforms allow you to explore graph metrics within an hour of downloading everything. On Gabor's point about the LDBC, if you were to go into the GitHub repo or hop into the LDBC Slack or message Gabor and I directly, there's a wide community out there of people that are always happy to help in this space.
Do you think we're doing enough at uni to train people up for this? Because it seems like a very important subject.
So I can only speak from the QM perspective, and I'd say not really.
The discrete mathematics and algorithms classes do a good job at covering the graph algorithms. Like everyone knows what a breadth first search is, or most people have heard about PageRank and connected components, but usually this doesn't extend to property graphs. The closest you can get is the object-oriented model that people learn in software engineering. So that's kind of a good conceptual basis to think in terms of entities that are connected to each other. And people also tend to learn ER modeling, entity relationship modeling, during their database courses. So you can kind of pick up the conceptual bits and pieces, but it's very difficult to tie these together in a coherent conceptual framework.
Okay, well, thanks very much for this very exciting discussion today. I think we could probably go on for a few more hours, but I don't think we want to bore the listeners too much. So I thank you very much for your time and all the best for the future.
Thank you very much, Peter, and thanks for inviting us back as well.
Thanks for having us.